The purpose of this video is to characterize the behavior of structural elements with pre-existing cracks. The discussion includes crack initiation, the degree of damage, and whether a structural member can tolerate it using the basic principles of linear fracture mechanics.
So, what does fracture mechanics mean to us?
Well, fracture mechanics is defined as the approach to evaluate the fracture behavior of structural members characterized by pre-existing flaws or notches. Okay, what are the design information needed to accomplish this approach? There are 3 pieces of information are required. Number 1. The nominal stress on the member, which can be obtained from structural analysis. Number 2. The fracture toughness of the material as obtained from fracture mechanics tests. Number 3. Flaw size and geometry of the structural member being analyzed. Well, how can we include these 3 requirements in the context of the fracture mechanics methodology? We'll get into this, but before we go further, let's go through some basics. First, let's discuss the cracking problem in structures as explained in this chart. Cracks can occur due to corrosion or fatigue. Corrosion is the gradual destruction of materials by chemical or electrochemical reactions with their environment. On the other hand, fatigue cracks are small flaws existing in metal due to imperfections in fabrication. They grow under repetitive loading such as wind and live loads, and under the effects of service loads, there will be stress corrosion cracking, wherein the growth of crack is assisted by the surrounding corrosive environment. Similarly, fatigue cracks will grow further with the assistance of this environment. Eventually, crack growth will extend to a size that cannot be tolerated by the fracture toughness of the material, and brittle fracture will occur under stress levels that may be lower than the design stresses. This may cause structural failure in some cases. Since we mentioned the expression brittle failure, let's discuss the possible failure modes in metals, which can be either ductile or brittle. This classification is based on the ability of a material to experience plastic deformation. Ductile fracture is characterized by large plastic deformation ahead of the crack. In addition, there is strong energy absorption prior to fracture, as well as significant deformation at the fracture surfaces, including twisting and tearing. Brittle fracture, in the contrary, is characterized by little plastic deformation, and the direction of crack motion is very nearly perpendicular to the direction of the applied tensile stress. The crack in this case is defined as unstable because it propagates rapidly without increase in stress. Let's now discuss brittle fracture of cracked members. The 3 basic modes of crack surface displacement are: Mode 1, opening or tensile mode. Mode 2, sliding mode. And Mode 3, tearing mode. It is important to note that in isotropic materials, brittle fracture usually occurs in Mode 1. Therefore, our discussion will be limited to this mode. Before we get to the fracture mechanics methodology, let's discuss 2 more terms: the toughness of the material and imperfections in fabrication. Toughness is the ability of the material to absorb energy, when loaded slowly, and defined as the energy of mechanical deformation per unit volume prior to fracture. It has a unit of inch-pound force per cubic inch. It can be characterized by the area under a stress-strain curve and a slow tension test. It is evident from a comparison of the 3 types of steel in the figure that the medium carbon steel is the toughest and the high carbon steel is the strongest. It is very difficult to fabricate large welded structures without introducing some type of imperfection in the form of notch, flaw, or discontinuity. The types of flaws that can occur in a steel welded detail are partial penetration and lack of fusion, porosity and inclusions, and undercut or microflaws at the weld toe. Now is the time to discuss the fracture mechanics methodology. An applied stress may be focused or amplified at a crack's tip. The degree of this amplification is dependent upon the orientation of the crack. The maximum stress, sigma m, occurs at the crack tip and can be calculated as a function of sigma, the magnitude of the nominal applied tensile stress, a, the length of a surface crack, or half the length of an internal crack, and rho t, the radius of curvature of the crack tip. This is a fundamental finding that will help us comprehend linear fracture mechanics. Irwin in 1957 defined the stress intensity factor for infinite width plate containing a through thickness crack with this equation. Since brittle fracture usually occurs in mode 1 for isotropic materials, then K will be further denoted as K1. In the context of fracture mechanics, the calculation of K1 is analogous to evaluation of the stress demand in traditional structural analysis and represent the driving force. The solutions of the stress intensity factors have been obtained for a wide variety of problems. For finite width plate containing a through thickness crack, the equation developed for infinite width plate is multiplied by a factor, which is a function of both the crack size and the width of the plate. When dealing with a finite width plate that has an edge crack, the same equation is applied. The function factor that is added to the equation is the only modification. Note the 1.12 in the equation to account for the fact that the edge crack exhibits 12% increase in the value of the stress intensity factor than the case of a plate with a through crack. Additionally, the function factor changes to assume this form for a plate with two edges. And this is how the function equation looks for an edge crack in a beam under bending. Now that we know how to estimate K1 for each of the several notched plate cases we looked at, we also need to keep the applied stress intensity factor K1 below a limiting value that indicates the material's fracture toughness to avoid brittle fracture. We are going to use K1C for it. It has to be obtained from fracture mechanics tests. When testing for fracture toughness, two specimens are most frequently utilized: the 3-point bend specimen and the compact tension specimen. The 3-point bend specimen is shown here. The material's yield stress, sigma sub cis, and the specimen's thickness are used to express the fracture toughness capacity K1C. The compact tension specimen is shown here. In both tests, the engineers select the thickness, B. W generally is set equal to 2B, and the final crack length, A, generally is set equal to B. The American Society for Testing and Materials Standards provides the guidelines for fracture toughness testing. This standard covers the determination of the fracture toughness KIC of metallic thick plates under linear elastic, plane strain conditions. Let's take an example. The dimensions of the mechanical tool depicted in picture are: D equals 250 millimeters, B equals 60 millimeters, and thickness T equals 25 millimeters. The fracture toughness test revealed a value of KIC equals 59 MPa square root meter. We would like to determine the magnitude of the fracture load P for a crack length of A equals 5 millimeters. In relation to the crack, force P is operating at an eccentric point. As a result, the tool experiences both axial load and bending at the crack portion. Therefore, we need to use superposition of two cases: case of finite width plate containing an edge crack, and case of edge crack in beam and bending. Therefore, for the crack length of A equals 5 mm, and A/B of 5/60 is equal to 0.0833. The geometric factor or the function equation for the axial force is 1.163 and for bending 1.047. By using superposition, the stress intensity factor can be calculated using this equation. And by substituting, the maximum load to be applied shall not exceed 26 kN to avoid fracture. This brings the video to an end. We introduced linear fracture mechanics, focusing on stress intensity factors and how to use them to manage metal fracture and cracks. Here are some recommended references to read later. If you would like to be notified when new videos are posted, please subscribe to the channel.